Welcome to this web lecture on heuristics for the transportation problem. So now I'm going to walk you through 3 different heuristics that you can use to solve the transport problem, which we introduced in a previous web lecture. So first of all, let's look into the case again. So we have TUE bike sharing system, which has bikes at different locations throughout the campus. And due to the fact that people can rent bikes at one location and drop them off at a different location, we must rebalance the bikes. So we must move bikes from one location where we have more bikes than we need to another location where we currently have a lack of bikes, so too few bikes, and all of that at as little cost as possible. In a previous web lecture, we modeled this as a transport problem using this instance with Atlas and Gemini as sources and with the Auditorium, Luna, and Vertigo as sinks. So now let's look into what a heuristic is, and for that we're going to refer to the paper of Laguna and Marti in 2013. So what they say is that a heuristic is a well-defined, intelligent procedure based on intuition, problem context, and structure designed to find an approximate solution to an optimization problem. In contrast with exact methods that are designed to find optimal solutions, heuristic methods find solutions that are not necessarily optimal. So a few things that you have to take away is, first of all, it's an algorithm, and secondly, it's not necessarily optimal, which doesn't mean that we can't find an optimal solution every once in a while. The thing is just we can't know if it's actually the optimal solution. We just know it is a solution, and that's it. We have to live with the fact that it might not be the best solution that we can find. So a heuristic is an algorithm that finds a solution and is not necessarily optimal. And an algorithm, again, is a systematic procedure that produces in a finite number of steps the answer to the question or the solution to a problem. So in our context, an algorithm is a problem-based approach which gives us an unambiguous set of instructions. So the unambiguity is extremely important. That also terminates eventually. So we don't want an algorithm that runs until the end of time, because that doesn't help us in finding an answer to the question that we've been asking in the beginning. And we're using heuristics as compared to exact algorithms because they're often faster than exact methods. There's a lot of cases where optimality is not necessary. So if, for instance, if I have a problem for which I need a solution in 5 minutes and I can get the optimal solution in 3 hours, then the time in between is just costing me too much. And sometimes heuristics result in easier to understand solutions. What I would like you to keep in mind is that this is definitely not always true, but sometimes it helps us to structure solutions in a way that they're humanly understandable. So the first heuristic that we're going to look into is the so-called northwest corner rule. So the first thing that we're setting is we're setting all supply and all demand to the actual values, and then we say we're starting with I equals 1 and j equals 1. And I promise you this will become a lot clearer once we actually look into the example. Then we satisfy as much of the demand as possible if supply remains, and then move to the next sink. If demand remains, we move to the next source. And then we terminate once all supply is depleted or all demand is met, or both. So let's look into an example because that will make things a lot clearer. Yeah. So let's look at this one example of this TUE bike sharing system, which has the sources Atlas and Gemini, which are here in the vertical direction, and 3 sinks, which is Auditorium, Luna, and Vertigo, here on in the horizontal direction. And now what we're doing is we're always going from northwest to southeast in this table. So we're always starting in the top left corner with Atlas and Auditorium, and we satisfy as much as possible, which in this case is a demand of 8 at Auditorium with 8 of the 15 supply that we have in Atlas. So we have 5 times, because that's the correct cost of direct shipment from Atlas to Auditorium, times 8, which is the minimum of 8 at 15, which is 40, which is the cost that we have so far. Then we move on with in the next building, which So we cannot move on to Gemini yet because it doesn't make sense because Auditorium is already fully satisfied. So now we're moving on to Luna. So in Luna, we have a demand of 11, while at Atlas, we have a supply of 7 left. So we satisfy as much as possible from Atlas to Luna, which is 7 items, which means that our supply in Atlas is completely depleted and we have a remaining demand of 4 in Luna. Now we move on to the second source. So we're moving on to Gemini and we're satisfying as much as possible from there to Luna, which is 4 because we have a remaining demand of 4 in Luna. So we satisfy those, which means that now in the final step, we have a demand of 6 in Vertigo. We also have a supply of 6 in Gemini, so we satisfy those. And this gives us a total cost of 158. Let's continue with the second heuristic, which is the color minimum rule. So in the color minimum rule, the first step that we're doing actually looks not too different. So we're also setting our O hat and our D hat to the same as in the northwest corner rule. But now we're only setting our J to 1, not our I. And now we're first finding the cheapest source, which has some slack capacity, and satisfy as much demand from there as possible. And if demand is satisfied, we move on to the next sink. And then we terminate once all supply is depleted or all demand is met. Similar to the previous example, this will get a lot clearer once we actually look at the example of the TOE bike sharing system. So once again here, we're having Atlas and Gemini in the vertical direction, and we have the sinks, Auditorium, Luna, and Vertigo on the horizontal direction. So now we're starting with Auditorium, and for Auditorium, we're checking which one is the cheapest. So is Atlas the cheaper or Gemini is the cheaper? And we see Gemini is cheaper. So we satisfy as much as possible from Gemini, which is the full demand, which is the full 8, which gives us a cost of 24. Then, since all demand is satisfied, we move on to Luna, which is our second sink. And we check which one is cheaper. And here we see Atlas is cheaper than Gemini, so we satisfy as much as possible from Atlas, which in this case is the minimum of 11 and 15, which means we satisfy everything from Atlas. Now we have a supply of 4 left in Atlas and a supply of 2 left in Gemini, which by the time that we move now to Vertigo means that we're just satisfying first the demand from Gemini and then the demand from Atlas, which then means, okay, all demand is met, all supply is met, and our total cost is 142. So the main difference to the previous algorithm is that we check which one is cheaper among the 2 options that we're having, which means that we see slightly lower costs in this case. So now let's move on to the third heuristic, which is the matrix minimum rule. So once again, the description of the heuristic actually doesn't look too different. So we first set the counters for supply and demand to the actual values. But then in the second step, we find the cheapest source sink pair with remaining capacity. So we're minimizing Cij such that the O of I is greater than 0 and the D of J is also greater than 0. And we satisfy as much demand as possible. And then we terminate once all supply is depleted or all demand is met. So also here, we're going to look into the example to see how we're actually doing these things. So in the matrix minimum rule, we're also, similar to what we've seen with the previous 2 heuristics, putting Atlas and Gemini as the 2 sources on the vertical direction and Auditorium, Luna, and Vertigo as the 3 sinks on the horizontal direction. Now we're checking which of those 6 entries in the matrix, so the 3, the 5, the 6, the 7, the 8, and the 9 is the cheapest, and the 3 is the cheapest. So we're satisfying as much of the supply and demand from Gemini to Auditorium, which is the full demand of Auditorium. Then we move on to the second cheapest, which would be Atlas Auditorium, but this doesn't help us anymore because here all of the demand of auditorium is actually already covered. Then we move on to the third cheapest option, which is Atlas Luna, and we satisfy as much demand as possible, which in this case is the full demand at Luna. So then we move on to Gemini Luna, which is the next cheapest option, but we also see that we have no demand left at Luna, so we satisfy nothing from there. Then we move on to the fifth cheapest option, which is the Gemini Vertigo at a cost of 8. And we satisfy whatever is left there, so we satisfy those two here. And then we move on to the most expensive option, which is Atlas Vertigo at a cost of 36. So this gives us a total cost of 142. So now we've seen three different solutions: the northwest corner rule, the color minimum rule, and the matrix minimum rule at costs of 158, 142, and 142 respectively. So now we're interested in how good these solutions are, or how bad these solutions are. So we immediately can see that the northwest corner rule is worse than the other two heuristics on this particular instance. So we immediately know that the northwest corner rule cannot be optimal, but we still have no idea if the other two are giving us a good solution or not. So what we would like to do is we would like to find a lower bound for the objective function, so something that is problem specific, that tells us, okay, we're definitely going to be better than this. So for instance, we're saying, okay, the optimal solution might be somewhere in this range, and we know that this other value, for instance, the value is 0 in this case, is definitely better than the true solution. It's definitely giving us less costs. Because if we know that some value is giving us a better value than the optimal solution, and we know what a heuristic gives us, then we know, okay, what is the most gap that we can get where the solution is bad. So now let's check if we can find a lower bound for this problem. So one option that we're always having is we can always drop constraints. And in this case, a natural candidate is dropping demand or supply, which is really very simple in this case, because if we only have demand or if we only have supply, then we really just have to send them to the cheapest option to ensure that everything is covered. So if we drop the demand constraint and only keep the supply constraint, we have costs of 105. If we drop the supply constraint, we get costs of 138. So which of them is now the better bound? So one could say 105 is less than 138, but if we remember, we would like to find a solution that is provably better than the true solution. But obviously, if we want to be able to judge how good our heuristics are, we want to have something that is as close as possible to the true optimum. So we're going to choose the maximum of these two, so the 138, because we know that the objective function cannot get better than 138. So now we have a best bound and we have a heuristic solution. And that allows us to calculate the so-called optimality gap. So we're calculating the objective function of the heuristic, which is an upper bound to our optimal solution, dividing it by the objective function of the lower bound, of the best lower bound that we know, and we subtract 1. And if we enter those values that we're having here, so the heuristic solution of 142, divided by the 138 of the bound, and then subtract 1, then we get this value of 2.9%. One thing to keep in mind that is if you maximize, you have to reverse the bound and the solution. So you always have the higher value in the top and the lower value in the bottom. And now what I would like you to do is to calculate the optimality gap of the northwest corner rule just by using this, this function as well. So what I would like you to take away from this web lecture on the heuristics on the transportation problem is, first of all, what a heuristic is. Secondly, I would like to take away the northwest corner rule, the color minimum rule, and the matrix minimum rule. And what I would like you to do is to calculate the optimality gap. Thank you.